Okay, so what we'd like to do is use that idea of force buoyancy to figure out how much mass we can put in a container or a boat or any other object and still have it float. We don't want it sinking to the bottom of the ocean or other container. Okay, so here we have my container with 1 kilogram in it, and you can see that it is floating nicely with a lot of volume still outside of the fluid. So we can easily put more mass inside of this without having it sink. Okay, so let's see how we actually figure out the amount that we can put in. Okay, so we need the dimensions of our container. And you can see that the container is about 14.8 centimeters tall. And the container is about 14 centimeters across. Okay, so very similar dimensions. So we need to find our volume. We use our volume formula, pi r squared height. Make sure you work in meters. So you do half of 14, and then 14.7 actually is what we're going to use for the height. Okay, and then we work that out and we get a volume of about 2.26 liters, which is 0.00226 cubic meters. Remember, cubic meters is your preferred unit. In fact, it's the unit you have to use for volume as our standard. Okay, so now we have our thing in the water. We have force gravity pulling it down. We've got a force buoyancy pulling it up. And right now they're equal, but we can get a lot more gravity in there before this thing is going to sink. So as it goes down farther and farther below the fluid, the buoyancy gets stronger and stronger. And the maximum buoyancy, we'll call it force buoyancy max, would be the density of the fluid, the planet's gravitational field, and the total volume of the container. That would be the maximum when the entire container is practically all under the fluid. Okay, we're using Delsey water, which turns out not to be the same density as real water. It's about 995 kilograms per cubic meter. We're on planet Earth, and we saw we had a volume of about 0.00226 cubic meters. Okay, so you multiply these numbers together, and we get a force buoyancy of about 22.065 newtons. Again, that is not the buoyancy right here, but that is the buoyancy when nearly 100% of the object is under the fluid. All right? So we want to set that equal to the maximum gravity that we can handle. Once gravity gets bigger than the maximum buoyancy, this thing is going to sink. We then do mass times gravity is equal to that value. We solve it for the mass, and we get 2.25 kilograms. So that means that inside this container, I can put 2 kilograms and still be able to float. And actually, we're not quite sure of that yet, because we have to realize that this mass is not just the mass that goes in it, but that mass includes this mass itself. Buoyancy has to hold up this plus whatever's inside of it. So let's take our container and put it on the scale, and we can see that it is about 200 grams. So we said that we could handle 2.25 kilograms. That's 2,250 grams. We subtract off the container, and this thing can actually hold 2,000 grams plus about 50 more. Once we exceed that, we're probably going to have the ship go down to the bottom. All right, so let's take a look. So here's what it looks like with our 2,000 grams added. I am leaving the 50 grams out. I do want to give a little bit of leeway so I don't have it sink to the bottom. And you can see that no longer is there a lot of container out of the fluid, but instead you can see that at least on the one side, because this thing's not floating perfectly flat, almost the entire thing is underwater. So just a little bit more mass, about this much more, is going to bring that down to the bottom.